Now, if we have the function h equals f of g of x, we can get information about the chain rule even if we obtain just values from a table. So as an example, if we use the values in the following table, we can calculate, let's say, the values of h prime of 1 and h prime of 2. Okay, so let's actually go and check that in the board with the table. So what we want to do is use the fact that h is equals f of g of x, f composed g of x, and the formula of h prime being f prime of g of x times g prime of x to calculate the values of h prime of 1 and h prime of 2. But if we do h prime of 1, essentially what we're doing is f prime of g of 1 times g prime of 1. And similarly, if we're doing h of 2, we're doing f prime of g of 2 times g prime of 2. So we have a couple of values that we need to find out. We need to find out who is g of 1, and then who is g prime of 1. And so we can obtain those values from this table. Notice g of 1, if x is equals 1, g of 1 is 2. So we're going to obtain that g of 1 now can be replaced by 2. And g prime of 1 now can be replaced by 3. Now, once that we have that, we just need to figure out what is f prime of 2. Notice that obviously that means that we need to have the information about 2 here in f prime, and luckily in our table we do. We have f prime, and f prime when x is equals 2 is 7. So we have 7 times 3, and that's going to give me that h prime of 1 is 21. And similar for h prime of 2, now we need to know what is the value of g of 2. G, when x is equals 2, is 1. So we're talking about now f prime of 1, since g2 is 1, times g prime of 2. G prime in 2 is 4, using that value. And now we're back to checking what the value of f prime is. F prime in 1 is 5, so we get 5 by 4, and we get a 20. Okay. So this is the way how we approach using a table with some values to obtain and to play with the formula of the chain rule. Now, the chain rule can be used to generalize the idea of using powers. So as in the examples before, we can take a function that is any particular function g to a power p, and with that we're going to obtain that the derivative of that is just going to be putting down the p as in a power, subtracting 1 as in the derivative of a power, and then multiplying by the function inside, which is g prime of x. Okay, so let's take a look at now that the chain rule can be extended to more than one function, really. So we can have a multiple composition. So with this function that we have here, sine of e to the 1.3 cosine of x plus 1. This is a large function that is composing at least 3 functions. And we can essentially generalize that idea and just continue doing chain rule. So if we have y equals sine e to the 1.3 cosine of x plus 1. Well, if you identify really quick what is going on, then you can do the chain rule. So for example, the derivative of 1 is 0, so that's just not going to matter. And the main function is cosine, so you're going to get cosine of whatever the function inside is. So cosine of 1.3 cosine of x, then multiply by the derivative of the function inside. But now the function inside is an exponential, so the derivative of the exponential is the same, e to the 1.3 cosine of x. But now this, notice, is composed with the function 1.3 cosine of x. So I need to multiply now again by the derivative of the function inside. And the derivative of the function inside is just going to be minus 1.3 sine of x. Okay, so this is the whole process of the chain rule. And that is, if you have the ability to very quickly see the compositions, you can just directly go and do that. If you want to see this as a composition of functions, then you gotta be careful. And so you can say instead, well, let's do this sine of f of x plus 1. Okay. So now you can say, okay, so let me use chain rule here. So y prime is what? Cosine of f of x times f prime of x, right? But who's the f of x that I'm talking about? I'm talking about f of x being e to the 1.3 cosine of x. So I can just go back and now replace that here. Okay, so cosine of e to the 1.3 cosine of x, right? But now who f prime of x is? And so that leads me to do the derivative over here. Oh, but we have a chain rule here as well. So we need to do e to the 1.3 cosine of x, because that's what the derivative of an exponential is. It's just the same function, compose whatever the function here is. Okay? Or you can see this as e to the g of x, right? If we wanna generalize this even more, and we can see it as e to the g of x times g prime of x, right? But then later, oh, okay, so who g is? Well, g is 1.3 cosine of x, and so that means that g prime has to be minus 1.3 sine of x. And then at this point, we return back here, and we plug all the chain rules. So it pretty much depends of how you want to do this. If you have a very big chain rule going on, then it might be a little bit cumbersome. Let me give you another example of something that can have multiple chain rules. So for example, if I have y equals the square root of 1 plus the square root of 1 plus the square root. Okay, so there's a big composition here. The big function is always the square root, and so y prime here is going to be 1 over 2 square root, and then everything that is inside, 1 plus the square root of x, times the derivative of whatever is inside. So what is inside? 0 plus, and then now the derivative of this one, which is 1 over 2 1 plus the square root of x. And then at that point, then I just did the derivative of this, plug this, and now I need to multiply by the derivative of the stuff inside, which is 0 plus 1 over 2 square root of x. So parentheses and parentheses here. Okay? So you see the idea of how this chain rule can work if more than one function is involved. Now let's take a look at some other examples where what we're doing is involve other operations. So for example, we use powers, but we also using quotients, and we're using product rules combined with things that have chain rule as well. Okay. So let's go with the first one. Y equals 6x cubed plus 3x plus 1 to the 3 halves. This is just an example of using the power, the generalized power rule now with the chain rule. So y prime is going to be, and now I'm just going to go ahead and do the chain rule directly without identifying the functions, this will be the ideal way of doing this. So now this is a power to the 3 halves. So I put down the 3 halves. I leave the same thing that is inside. Subtract 1, so I get to the 1 half. And now I multiply by the derivative of the function inside. So that's going to be 18x squared plus 3. And that's it. This is the end of this example. Of course, if you had the ability to simplify, you should do so, but a lot of the times you're not going to have that chance with big chain rule situations. Now, if you have y equals x squared, square root of x squared plus 1, notice that this is a power situation as well. You can think of it as x squared plus 1 to the 1 half. But if you're getting used to use root and the derivative of the root, then you can go directly and work in that way. In this case, y prime is 1 over 2 and then the root, right? Like any derivative of the root. But now we compose with x squared plus 1, which is the function inside. And then we multiply by the derivative of x squared plus 1, which is the function inside. And that derivative is 2x. Okay? And so that is the solution for number 2. Now, number 3 is a little bit more involved because it's going to have a quotient rule playing. But the basic derivative is a chain rule. Notice we have y prime. This power is going to go down 3, and then we plug the function inside as usual. 3t squared, 5t squared over 3t squared plus 2. And now this is going to be to the 2. But now we multiply, and here's where the quotient is going to play. It's going to play when we take the derivative of the function inside. So we have 10t times 3t squared plus 2 minus 5t squared times the derivative of 3t squared plus 2, which is going to be 6t, over 3t squared plus 2 the square. And of course, in this particular scenario, you definitely can simplify things. And that's going to be better, especially if you have to do maybe multiple derivatives. So 30t cubed plus 20t minus 30t cubed over 3t squared plus 2 squared. So notice you get to cancel this part, and now you have this. Which will be a lot better if we have to do something like a second derivative, which will give me a product rule with a chain rule, with the quotient rules. So this example, doing a second derivative will be very messy. Okay, I encourage you to actually try and do it just for practice. Now the last one is just a product rule with a chain rule. So not that complicated really. We have y is equals the derivative with respect to x of x squared plus 1. So it's a little bit of the one before plus something extra. So here's a product rule initially. That's the base. So the derivative of x squared to x by the second function with a derivative plus the x squared times the derivative of this. And now we got this one from the second problem here. So we know that this is actually this function. Okay. So that concludes the examples here that we have for part 2 of the derivative. In part 3, we'll see some more examples of different situations.